Can you hear me, everyone?
Yes, sir.
Okay, so from here, you just have to learn the motivation, okay, behind using push pull. Why do we go for push pull and why we don't go for open drain? Okay, why is why do we always choose push pull as the output type? What's the problem with open drain? What exactly is the problem with the open drain? So this slide tells you what's the problem with open drain. Okay. You can see whenever this output bit is 1, what happens? The controller inverts it through 0, and 0 enters the gate terminal of the MOSFET. This is an NMOS, so that's why your MOSFET turns off. Whenever it's off, you replace that using an open switch. Now you see, whenever you have an open switch here, it causes this output to float. Okay, so the output, um, whenever this output bit is 1, the GPIO pin has a high impedance to the external circuit because of this open NMOS. Right, so you want the output at the output pin to be 1, but it has a high impedance value. Right, so this is not something you want, right? So that's why we never use open drain as the output type. We always go for push pull. Generally we always go for push pull. Okay, so for this kind of a scenario, push pull is applicable or preferred. Right, you can see that this pin offers a high impedance to the external circuit whenever the output bit has a value of 1. Okay? That's basically the motivation of using push pull instead of open drain. And finally, we talked about the slew rate. Right, there can be different speeds at which the signals transition. Right, what's the problem with the high GPIO speed? How to configure the speed? Right, which speed to use? So it depends on the application, right? So if you're toggling LEDs, you would like a low speed. If you're using a low speed peripheral or a slow peripheral, you would want a high speed for the transitions. Okay, so you have to configure or decide the speed based on the peripheral speed. So we saw that. We saw what was slew rate, right? And so here again, it repeats the difference between push pull and open drain, right? So you can see when the output bit is 1, push pull gives you a 1. When the output bit is low, push pull gives you a low. So this high and low are at the pins, okay? At the pins. So when the values are valid internally, the values are also valid at the pins externally. Okay, but that thing doesn't happen with open drain. Open drain, you can see that whenever output bit is 1, at the pin you get a high impedance value because the MOSFET was open. We replaced that using an open switch that offers a high impedance value, high impedance to the external circuit. Okay, that's why we don't go for open drain. Internals of ODR, we already talked about ODR, how it can be used to uh, control the value at a particular pin. So for the exam, you would want to revise this code. Okay. how you can turn up the LED, what are the steps, right, and the expressions that are used. So here, what's important? The steps. What do you have to do one by one? Okay, enabling the clock, setting the mode, setting the output type, and then finally setting the output value.
Uh, Sir, for the dual, does it mean we have to end the 3,
For which line?
the second line?
Yes, second line. You have to end with not 3. Okay, not 3 means not 1 1, which is actually equal to 0 0. Is that clear?
So basically bitwise of 4 with 0 0.
Bitwise and with 0 0. No, bitwise and with the data in bits 4 and 5. So remember, the modar register has 2 bits for one pin.
Yeah,
So because you have a 4 here, it's referring to bits 5 and 4. If you look at the internal structure again, that would be clear. Things would become clear. Okay, whenever you're saying 4, you're actually referring to the data in bits 4 and 5. So whatever you data you have in bits 4 and 5, you add that data with 0 0.
alright, now it's clear. Thank you, sir.
Okay, so yeah, so this lines basically tell you which are the registers you need, which port you need, which clock you need. Okay, this tells you that you need the modar register. You cleared the bit first and then you set a bit to 1 in order to convert to the output mode. Then you set the output type. Then you set the value in the ODR register, either to a high or to a low. Because in this case, you want to light up the LED, you want your output to be 1, right? A high. So that's like some finite amount of voltages that would allow a current to flow through the register and light up your a current to flow through your LED and light up your LED. Okay, that's why you want the output to be 1. Any questions regarding this? Internal structure. So for input, which are the relevant registers? For output, which are the relevant registers? Is the Schmidt trigger part of the input or the output? What are the all the possible modes? Right? What are the possible output types? Um, what can you do with the PUPDR register? Why do you sometimes use? When do you use this option? No pull up, pull down. Okay, when do you use this option? No pull up, pull down. It's when you have your pin externally pulled up or pulled down, so that then you don't need a pull up or a pull down internally. Okay, that's when you use this um, 0 0 state. Okay, no pull up, pull down. And if you don't have a pull up or a pull down externally, you would want to have a pull up and a pull down, or a pull down internally. Okay, why do you need this pull ups, pull downs? Is to avoid any high impedance value internally. Okay, so for whenever you're talking about the output, which are the registers that play a role? The mode register plays a role, the output type register plays a role, the output data register plays a role, and the PUPDR register plays a role. Whenever you're talking about the input, which registers play a role? The input data register plays a role, the PUPDR register plays a role. Okay, and your Schmidt trigger is actually part of the input network. What are its functionality? We discussed that it reduces noise, it improves the slew rate. Okay, and how is noise inserted or incorporated into the system, why is the slew rate slow, what kind of an output does a comparator produce from this input signal, from a keyword input signal and threshold, how is the output produced, and how is the Schmidt trigger different from a comparator, in that because you can see the comparator only compares with one threshold level, whereas the Schmidt trigger compares with two different threshold levels, threshold high and threshold low, which forms an immunity band. Right? So you can see that the Schmidt trigger output is different from the comparator output, right? And any fluctuations within the immunity band is ignored for a Schmidt trigger. Internals of the peripheral enable clock register, right? How do you enable the clock for any port? You define a macro like this. RCC is actually representing your reset and control clock module. And then this is the name of the register that has the clock information for the peripheral clock. This is the register that you use to enable a particular clock. So I think this is what we discussed last class. So it was like pretty recent. Anyone has any questions from slides 15 to 31? This is what we discussed last class. I mean, the keypad scan is kind of simple, right? The keypad scan is kind of simple. But before that, any questions regarding this joystick configuration? So you'd want to look at this piece of code for the joystick.
So what can we expect from here?
So the steps that are involved. Also, if you are given a configuration, how you would read the input from a pin. Okay, so here, what was the configuration? Your center button was connected to this pin, right? And your center button was connected to this pin. So if you wanted to read the input, I mean, whether the center button was pressed or not, if you want to detect that, you need a piece of code, right? Similarly, for all the buttons, if that was pressed or not, if you want to detect that, you need a piece of code. So this is the code to determine whether the center button was pressed or not. Okay, so if I give you a similar device like a joystick and I say this button is connected to this pin, how would you read the input at that button, whether it was pressed or not? Something like that. Okay, I might change the name of this button, change the name of this pin, and but basically ask the same question. I mean, that's a possibility. I'm not saying it will come up, but this is the type of questions you might see. Or just what are the relevant registers involved? You might ask what are the relevant registers involved. Here, what are the relevant registers? Your clock enable register is a relevant register. So it's a HB2 peripheral clock enable register. So that's a relevant register. The mode register, the PUPDR, right? The IDR. IDR is called the input data register. Since here you're detecting an input, IDR register comes into the picture, the input data register. So what are the registers involved? Okay, that could be a possible question. I could give you a piece of code and tell you what a particular line, ask you what a particular line is doing, right? And why do you need that line, or what is a particular thing representing a value. So it's important that you have the concept clear. Okay.
So basically, we should know how to write the code and what the code does.
Yeah, correct. So how you read the input from a pin, okay, because a pin is actually connected to a button, right? So whether the button or was pressed or not, you get an idea from the value in the pin, okay. For this case, how did you know if the button was pressed? You actually read pin 0. You read the value from pin 0. How do you read? Using this line, okay. You're reading the value in pin 0, and from that value you can actually determine whether the button was pressed or not. And this 3 slides basically show you the internals of the relevant registers relevant to the input, right? Whenever you're using the pin as an input pin, what are the relevant registers? The clock enable register, the PUPDR, and IDR. So of course you would need IDR because IDR actually contains the input values. It contains the values of the signals that enter the input pin. Okay, so that's important. IDR, PUPDR, and clock enable register. You would want to see the internals and how they function basically. So anyone has a question regarding this clock enable register or the pull up pull down register or the IDR?
No, sir.
Is it clear what these 3 registers do? I mean, we discussed this last class, right? So today's Monday. So yesterday, yeah. So we had a discussion on this yesterday. So it's pretty recent. So I'm not delving into the details because, right. So just giving you a hint of what could come up from which chapter, right? So we discussed this module 10. From module 5, what could come up? Instruction to machine code conversion. Okay, as simple as that. Instruction to machine code conversion. And for the data transfer instructions, for like load and store instructions, you might be given something like a memory map with all those rows, different memory locations. I might ask you to fill that up, or it could be partially filled up. And I might ask you something about the data that is there. Okay. And right, so we kind of had a discussion on everything that's there in the syllabus. So any final questions or any topic, any concept that you didn't understand, that's not clear? Anyone? If not, let's move to the attendance for today. Jahid Hassan, are you there? Jahid Hassan. Adnan, you're there, right?
Yes, sir, present.
Alif Jordar.
Present, sir.
Mohammad Samir Hussain. Asaduzzaman Limon. Sabrina Akhtar Sabina. Sani Ahmed Shravani, Asmaul Islam Tisha,
Present, sir.